For this tutorial series, I'm going to be talking about digital forensics with a focus on the Windows operating system. So before I dive into the technical details of digital forensics, first and foremost, I want to get a definition of what forensics is generally. Generally, forensics encompasses the set of methods in which we try to place blame for a crime on a person, entity, organization, or whoever committed that crime. So in this example, we see that someone committed a crime by stealing Equifax data. Somehow that crime was detected, and through our forensics analysis denoted by this Scooby-Doo, we figured out that it was this person that committed the crime, and then whatever happened to that person after that detection is up to the justice system. So in typical forensics, we typically think of TV shows such as CSI, in which they analyze evidence such as blood splat patterns or DNA analysis or bite mark analysis, whereas in computer forensics, nothing physically happens. So what is our evidence? Well, our evidence is what the criminal did, which is embedded in the memory of the system. So everything the attacker did leaves some kind of trace in RAM or the hard drive, depending on what they're doing. So here on the left we have RAM, and RAM is typically characterized by it being volatile. And what I mean by volatile is that as soon as the computer is turned off, once the RAM doesn't have any more power, all the data that was stored in the RAM is now lost to us, which really sucks from my perspective, because that's the data we want to analyze to try to detect that a crime has happened. And some things that RAM might contain is kernel data, runtime data, and short-term memory. Basically just anything that you don't need for a while. It doesn't matter if you had that data a year down the road. Whereas here on the right, a hard drive takes a much different approach to how it stores memory. A hard drive is more interested in storing data for long-term usage, such as your thesis for your PhD or something. So, from our forensics perspective, what can we extract from these memory devices? Well, like we said before, RAM is more interested in the short-term memory, so things that we might be able to analyze from it are open sockets and files that a process has, a list of the processes that are running on the system at the time of the dump, and logged on users. So in general, RAM is going to let us peer into what the system is doing at the time of capture. And something I'm going to emphasize in the next slide is that as soon as you detect a crime has occurred, you need to dump RAM immediately, because the evidence that the criminal left behind may become fleshed out from new data, because like I said earlier, RAM is more interested in holding the short-term memory that you don't need for a while. Whereas over here on the right with the hard drive, the contents of the system aren't going to change drastically, but that's not to say that you don't want to make a dump of that hard drive as soon as you detect a crime, because a criminal may be able to change the contents really quickly. So you want to dump both as quickly as possible, but it's definitely more important that RAM gets dumped first. So now we're at this point. Let's say that we're at this company and we have just detected that a data breach has occurred. So that's going to be denoted by this caution symbol. The first step we're going to do is we're not going to unplug the computer, because like I said before, once you unplug that computer, all the evidence that criminal may have left behind in the RAM is now lost to us. And I know that this pulling the plug may be something that's really first nature to someone, because if someone's currently in your system, it makes sense to pull the plug so that they no longer have access. But from the forensics point of view, we want to keep that computer powered on as long as possible. Then, as soon as we don't unplug the plug, we're going to dump the unpaged memory contents to disk. And what I mean by unpaged is that virtual memory, which is how most computers deal with RAM, virtual memory allows you to store some of the contents of RAM onto the disk for better utilization of the RAM. And because that little piece of memory is on disk and not RAM, we can't really dump it with today's tools. And then once we dump this memory, we're going to take that dump and we're going to analyze it here, denoted by this guy on the computer. So there's two ways we can try to analyze this data. The first way is to have an absolute intimate knowledge of the operating system, architecture, everything there is to know about that memory dump, or we could take the much easier path and use a tool. The most popular tool I found with RAM memory forensics is volatility. It's just a tool that's the combined effort of government, academia, and industry to provide some kind of common framework to work on to do these things. And volatility has that intimate knowledge of Windows 10, 8, 7, pretty much every operating system you can think of that's in major use. To date, the latest version is 2.6, which was December 2016, written in Python, and that's about all there is to say about volatility. Before we dive into how to use the tool, I think it's helpful to actually see what the tool is doing so that you can have a better understanding of what's going on. And also, at the end of the day, someone has to write the tool, so someone has to understand what's going on here to make the tool in the first place. So let's consider the common forensics case where we have a process and we want to see all the resources that that process is utilizing. Well, to do that, it's quite a lengthy process, and what we're going to spend the rest of this presentation doing. So here we have our process image in RAM, and we want to look at a little section of it right here, and this is the process handle table. The process handle table is the process's way of requesting resources from the OS and the OS giving you access to those resources. So here at index 0, it points to kernel data for a file, which allows us to make that switch into kernel mode and do whatever operations we want to on that file. On the first index, we point to a socket, and on the fifth index, we point to a registry key. It just so happens that in this example, the other indexes aren't utilized. So what exactly is this pointer pointing to? Well, in the case for the 0th index, it's pointing to the kernel metadata for a file, not the actual file itself. The reason for this is because we want to separate the permissions and other metadata that we open the file with separate from the actual contents of the data. So all of these kernel metadatas for the file, the socket, and the registry key are called Windows Executive Objects. A Windows Executive Object has this form. It starts with optional object headers. We can have 1, 0, or we can have more, denoted by this ellipse. And just like the name implies, they're optional. You don't have to have them. And then after that, we have an object header, which for a Windows 7, a Service Pack 3 operating system is always going to be 30 bytes. And we describe the object header in more detail in the next slide. Right after the object header, we have the object body. And I want to stress again that if this executive object happens to be a file, for instance, the object body is not going to contain any of the file contents. Instead, it's going to contain the metadata that the kernel's interested in, such as the permissions that you opened it with, read or write, execute, those kind of things. So with that out of the way, the object header is interesting because it can tell us a lot about this particular executive object, and we're going to look at it in this slide. So this isn't an exhaustive list of the data members that's included in the executive object header, but it's some of the more interesting ones. We have a pointer count, which I want to specify here that your user program will not have any pointers to this object header because it's in kernel space, and for security reasons, userland programs cannot access kernel space programs. If you want to know more information about that, you can just look up the difference between user space and kernel space. Here we have a handle count, and this is useful, for instance, if we have two processes that are both accessing the same file. The handle count here would be 2. And in the case that one process closes their handle, this handle count will be decremented to 1, and then when that process closes its handle to this file, it'll be 0, in which case the operating system can say there's no handles to this object, we can mark this to be free. The next data member we have is a type index, and this is kind of hard to wrap your head around because it specifies the type, but the actual data it stores is simply as an integer. So I have a picture here to help with understanding it. If this block is the object header, this particular section of it is the type index. And let's say in this instance it's 1. Well, this 1 is going to be used to index into some kernel global array with object type objects, and I get into that into the next slide. And because it's a 1, we're going to index into the 1 slot of this array, and it says that this is a process type. So we know that this executive object is describing the kernel metadata for a process. And then the last two object header attributes I have listed here is info mask, is what just specifies what optional headers are present, if any, and then a security descriptor, which describes the security restrictions for an object. So now in the next slide, we're going to be analyzing a object type object, which is a particular instance of this array. So file is an object type object, process, socket, and register key. So this, again, isn't an exhaustive list of all the data type or all the data that is contained in an object type object, but it's the most interesting to us forensically. Total number of objects, which is the total number of processes. The process object type object will contain the number of processes that are on the system. The file object type object will contain the number of files. And similarly, the total number of handles, the number of handles to these objects. And then type info is also interesting to look at because it specifies whether this particular object type is paged or not. So let's consider the case where the file object type object type info says that files are unpaged. For us forensically, that would be good because that means that all the file objects in kernel memory will always be in memory. They won't be swapped to disk. So whenever we get this memory dump, we know that we have every file executive object there is to have. Whereas consider the case where type info specifies that it is a paged object type. That means that in a particular memory dump, we'll never know if we have every single file object. It's very likely that some of the file executive objects are actually on disk and we didn't get to dump them when we dump the memory. And then the last data type or data that's specified in object type objects is the key. And a key is just a 4-byte tag which uniquely identifies object allocations of this type. And this is used in the next few slides. But basically, you can think of a file key being the words or the word file, F-I-L-E. Process is proc, P-R-O-C, and useful acronyms like that for the rest of the object types that you can have. So we've covered a lot of ground, and it's useful to have a summary. So here's basically what we've gone over. We have a process image here, and we're going to look at a section of this process which contains the handle table. And the handle table is the resources that we have allocated from the operating system. The operating system gave us access to and filled our handle table with pointers to the executive object in memory. And the executive object is the kernel metadata for whatever resource we've allocated. And I'm going to keep this really generic, so I'm not going to specify any particular types. If we look at the executive object, we have an object header here, and we have the body over here. If we look at this little section of the object header, it's the type index, and it's going to be indexed into the object type object array. And in this particular case, it contains the value 2. So it's going to take this executive object is of the type of whatever specified here, which could be file, process, socket, any number of things. So now that we've covered what an executive object is, what its header looks like. How do we allocate these things in the kernel memory? Well, in kernel we have a pool, and a pool is a section of memory that the kernel gives itself to allocate these things. So what we have here is from here down is the executive object we've covered previously. The only thing different between what we previously covered and now is we now have one additional header called a pool header. And the pool header is responsible for the allocation of data so that we make sure that we don't crisscross, or one object type doesn't cross another. It's all for allocation. So down here, these are some interesting data that's included in the pool header. We have the block size, which includes how big this header is, the pool type, whether it's paged or non-paged, and the pool tag, which is a 4-byte value which should uniquely identify. This is what was in the book, but I'm not sure if it's that useful. So you may be wondering, well, where is this pool tag going to be coming from? Well, if we go previously into what we covered here, an object type object contains a key, which is a 4-byte tag. So what's going to happen is when the kernel allocates something in this pool tag is simply going to be the tag that's specified in the object type object. So if it's a file, this pool tag is going to contain the letters F-I-L-E. If the object is of type process, it's going to be capital P-R-O-C, and so on and so forth. There's a somewhere on Windows documentation you can find what these executive object tags are. So now we have all the pieces to try to piece this together of what resources this process has. So let's walk through some code, or some pseudocode, to see what happens to allocate these objects. So first, the programmer makes a call to open file. This open file will call a bunch of different functions until it all eventually funnels into obcreateObject. obcreateObject will then go to the file type object and decide whether this object should be paged, among other things, and it's going to also grab that 4-byte type key and use that for the pool key. Then once it has all that data, it's going to call exAllocatePoolWithTag with the options it just gathered. And then once it's done that, you have that executive object in memory until you say you don't need it anymore. And that's the point I want to really clarify or emphasize here, is when you say you don't need it. The programmer should call closeHandle when finished with the file, but anyone who's done any kind of operating system programming before knows that it's very easy to forget that little tiny detail. So let's consider the case you don't close that handle. If you recall previously, when I discussed the handle count here, when the handle count becomes 0, this object will get put on the free list, meaning it's available for deletion whenever it's convenient. If I never call closeHandle, this handle count never gets decremented. This means that this object will never get deleted, which from our point of view as forensics analysts, this is very good, because this means that the criminal failed to clean up his crime scene, leaving a lot of evidence behind. But of course, from a performance perspective, that's very bad. Try not to do that. So let's consider the case that he did call closeHandle and the handle count is set to 0. What happens? Well, like I said before, it'll only get deleted when it's convenient. The operating system isn't going to fill that section of memory up with zeros. Instead, what it's going to do is it's going to add it to something called a free list, which tells the operating system that this section of memory is free for whenever future allocations are needed. This means that if you catch a crime happening at a really good time, immediately after it happens, chances are, depending on how busy the system is, you can dump that memory and still have that data, despite it being actually closed by the criminal. And this is also another reason why it's very important to try to get this data as soon as possible, because if you can beat it before another allocation happens, it's basically the same as him failing to clean up the crime scene. And so now I'm going to try to tie it all together graphically. So consider that we have open file or a socket call or something. We're wanting to create some resource from the operating system. So the first step is it's going to call a set of functions. And these set of functions will eventually always funnel into obcreateObject. obcreateObject will then go off through other function calls and get the data needed to fill the pool allocation up, because obcreateObject is only interested in, well, creating the object. Getting the data is going to be handed off to other functions. Once this figuring out the data is done, it's going to return back to obcreateObject. Then obcreateObject is going to call exallocatePool with tag. And that's just going to take the data that was collected here and actually put that on the memory. And then it's going to return obcreate, and then return up to our original function call. So this is the path taken to create an executive object, and it's surprisingly generic. It ties really well, I think. So, how can we see what resources were used? Well, like I said before, this pool tag is set to a very predictable value, the 4-byte value that's of object types. So if we go through and just scan for the string file through memory, just a top-down string look for file, chances are we can probably find most of the files that are on the system. But of course, only looking at 4 bytes could provide a lot of false positives, and that's where volatility comes in, and it semantically looks at the other data values to make sure that they make sense so that we can figure out if this is an actual allocation or not. In the next video, I'm going to show how to use volatility to actually look for the files that are allocated and what resources a process is using. And of course, if you would like to read further about this, this is the book I'm using, The Art of Memory Forensics, and the particular talk that the particular subject that I talked about today is in chapter 5 of this book.